In this video, we will learn about the difference between grid-forming and grid-following inverters. The idea of video presentation was chosen from among the ideas, and the video duration is 5 minutes. The difference is shown between traditional synchronous generators and inverter-based resources. On the left, traditional sources like coal and gas use synchronous generators to produce AC power. On the right, renewables like solar and batteries produce DC power. We need inverters to convert DC to AC because most loads run on AC. Traditional power systems rely on synchronous generators, or SGs, to provide voltage, frequency, and inertia. In modern renewable grids, inverter-based power sources, or IBPS, like solar and wind dominate. This shift introduces new stability and control challenges. Grid-forming inverter, GFM, acts as a voltage source and uses droop control. It can operate without the grid and provides virtual inertia, making it ideal for weak or isolated systems. It leads the grid by setting its own voltage and frequency. As shown in the diagram, it stabilizes the terminal voltage by controlling current through the impedance. Grid-following inverter, GFL, acts as a current source and uses PLL to follow the grid's voltage and frequency. It depends on a stable grid and cannot operate in islanded mode. It's common in solar and wind systems with strong grids. It follows the grid, it doesn't lead it. GFM challenges. 1. Needs energy storage like batteries or supercapacitors. 2. Requires advanced and complex control systems. 3. Poor coordination between units can cause instability. GFL challenges. 1. Needs a strong grid to stay synchronized. 2. Fails in weak or low inertia systems. 3. Cannot support voltage or frequency regulation. 4. Disconnects during faults, which may destabilize the grid. Top 3 GFM opportunities. 1. Can restart the grid independently after a blackout, black start. 2. Provides virtual inertia to stabilize low inertia systems. 3. Enables 100% renewable grids without relying on synchronous generators. Top 3 GFL opportunities. 1. Cost-effective for strong and stable grids. 2. Well-suited for large PV and wind systems connected to the grid. 3. Technologically mature, widely available, and easy to scale. GFM keeps voltage and frequency stable. When the grid shifts, it adjusts current, I, to maintain system stability. At 70% IBPS penetration, the system remains stable after disturbances. However, increasing penetration to 71% causes severe oscillations, and the system becomes unstable and unable to recover. Just 1% difference leads to a major change in stability. High IBPS penetration is expected in Europe by 2025, especially in countries like Germany and Portugal, requiring GFM for stability. Meanwhile, others like Sweden and Slovakia will have much lower levels. GFM replaces synchronous machines for voltage and frequency control. GFL can't work alone in high renewable grids. GFM brings stability in low inertia systems. Future grids need well-planned GFM deployment. Combining GFM for stability and GFL for delivery completes the grid. Summary of the two types of inverters. GFL controls current and follows the grid. GFM controls voltage and leads the grid. At the end of this video, thank you for watching. If you have any questions, you can ask.